We have Chapter 7, Radiographic Imaging in RAD 100. This chapter is going to go over a lot of very key concepts. This is going to be kind of starting a lot of the concrete foundation of our sort of x ray knowledge as we proceed in this class and this entire program. The four requirements exist for x ray. Just good to know these. The vacuum, which is the tube envelope. It's important to know that it's a vacuum, to know that when these electrons are proceeding through the tube, they're not interacting with any air. They're not colliding with air and having any issues with that. There also needs to be a source of electrons, which is the filament within the x ray tube. There needs to be a method to accelerate the electrons rapidly, which is going to be the voltage we're applying to the tube. There needs to be a method to stop the electrons, and that's going to be the target. For us, it's an anode target made out of tungsten. Here is a breakdown of it all. You have your filament. From the filament, your filament is going to have the electrons start forming on it through a process known as thermionic emission. These electrons are going to be sent towards this tungsten anode due to the voltage applied to the tube, and they're going to strike what's known as the focal spot, and x-rays are going to be produced. When this process happens, 99% of this process, it's just going to generate heat. But 1% of this process is going to be what creates the x-rays. And these x-rays are going to be able to exit the tube through the window. It's very important that these x-ray tubes have a window because the rest of it is enclosed. It's in a lead housing. Since whenever these electrons will strike this focal spot on the anode, x-rays are going to be produced in all sorts of ways. And we only want them to travel through just a window. Here's sort of a breakdown of types of radiation that can occur with just one exposure. You have your primary radiation. This is going to be the radiation that has left the tube before any sort of interactions occurred. You have absorbed radiation. This x-ray's hit a spot in this patient and just been completely absorbed in them. It's happened, you can see in multiple areas here. You have scatter radiation. The x-ray has traveled down. It's hit something in the patient's body and it's scattered off. This photon's gone away. Sometimes that scatter radiation can actually hit the patient and come at weird angles onto the receptor. Then we have what is most important for us for the diagnostic data, our remnant radiation. This is the radiation that has traveled through the patient and it's been able to strike our IR exposure, or strike our image receptor. Factors under radiographer control. These are often referred to as technique or prime factors. You have your mass, your KVP, and your SID. And we're going to get into each one of those individually. First off, starting with mass, this is going to be a product of milliamperage and time. Milliamperage is a measure of the electrical current passing through the x-ray tube. This milliamperage is going to get applied to the x-ray tube. It's going to get applied to the filament. And that MA is what's going to cause the electrons to start forming through thermionic emission. Time is the measure of the duration of the exposure. It can be represented in decimals, fractions, or millisecond values. But let's remember here, when we're talking about the mass formula, it's in seconds. So if something's given to you in milliseconds, we're going to have to do a conversion. Mass directly controls the quantity of X-ray beam photons that are produced. Doubling your MA is going to double your quantity, and the same is also true for your intensity. So if your mass doubles, your quantity doubles. If your mass is cut in half, your quantity is cut in half. Here are just some breakdowns of how you can convert your seconds and times if it gives you different ways. 1 second is equal to 1,000 milliseconds. So 400 milliseconds would be 0.4 seconds, so on and so forth. Some sample mass math. 50 MA times 0.2 seconds, 100 MA times 0.1 seconds, 200 MA times 0.05 seconds. I'll give you some time to do that. You can pause the video, and if you got 10 for all of these, you've done the math correctly. a little bit of a breakdown. When your MA goes up, when your milliamperage goes up, the number of X-rays produced is going to go up, your patient dose is going to go up, and your receptor exposure is going to go up. Your patient dose is going to go up because there's more X-rays. Your receptor exposure is going to go up also because there's more X-rays. Let's get into kilovoltage peak. This is the measure of potential difference, which is your voltage, forcing the current through the tube. This controls the penetrability, the quality of the beam, and this also affects the quantity of the X-ray photons produced. Let's break those down some more. Penetrability and quality, this is the bread and butter. This is the most important thing when talking about KVP, because none of these other prime factors we're talking about affect this. The quantity, which you can also say quantity and intensity go hand in hand, the quantity or intensity of the X-ray photons produced is also affected by your KVP. Let's go back to our tube here. So the current is applied. The current gets applied and thermionic emission is occurring, electrons are being produced. We now apply the voltage. If we apply a higher voltage, these electrons are going to proceed more rapidly. They're going to accelerate quicker. And when they strike these anodes, more incidence of X-ray photons being produced is going to occur. When we're talking about KV relationship to receptor exposure, KVP is proportional to the IR exposure, but the relationship is not linear like it is with mass. How in mass, whenever you double your mass, it's going to double your IR exposure, or it's going to double the quantity of X-rays. It's not true for KVP. For KVP, we use what's called the 15% rule to know that if you increase your KVP by 15%, you're going to double your IR exposure. If you reverse it, it's also true. If you reduce your KVP by 15%, you're going to have your IR exposure. This is a little breakdown word example. Feel free to pause the video, and I'll tell you the correct answer here. The correct answer is that you have to change your mass to 15, because since your KVP has went up by 15, it's went up by 15% of 100. That receptor exposure has now doubled. So in order to keep it the same, we have to have our mass. Just a breakdown of KVP. KVP increases, your quality, which is your energy, this is what's affecting your penetrability, is going to go up. The quantity or your intensity is also going to go up. Your patient dose is going to go up because now there's more X-rays going on. And your receptor exposure is also going to go up. Your source to image distance, your SID, this is the distance between the point of X-ray emission, which when it hits the anode, that spot is known as the focal spot, and the image receptor. This also is going to affect beam geometry and the relative intensity of radiation reaching the receptor. To break down how that's going to affect the intensity reaching the receptor, we have this example that we're going to go into about a flashlight. This is going to be our control. The flashlight's in the middle, and it's fairly intense right here at its target. And you can see the target is the image receptor. Now the flashlight has gone further back. It's not as bright anymore. The intensity's gone down. Now, in our case, the SID has increased, so the intensity has decreased. What if we reverse that? If we reverse that, the exact opposite is true. Now that the flashlight is so close to this image receptor, the intensity has gone up. So your SID has decreased. You have a lower SID, but you have a higher intensity. Here's just those three pictures all together so you can see the difference. Again, fairly bright, right in the middle of bright, getting kind of dim, much brighter. We, of course, have a fun math formula to go into this. This formula is known as the inverse square law. A lot of times, anytime you're going to be dealing with distance, in X-ray, we're gonna be hopping into the inverse square law formula. So please know the inverse square law formula. When you're seeing these subscript, these little lower numbers of 1, 2, 2, 1, this is your old number. So this would be your old intensity over your new intensity. And when it goes to the distance, it flips it. So your new density is over your old density. And with density, please notice these are squared. And just the way this formula works in practice, if you were to double your distance, it is going to reduce the intensity to 1/4. Because let's go back to the flashlight. If you double the distance of the flashlight, it reduces the intensity to 1/4 of what it was before. This here's a pretty good YouTube video. It also introduces another formula that you can use when using the inverse square law. If you want to look into that, you're more than welcome to use it or try it out, see what works better for you. But I would still fully know the original formula as well. We're going to be getting into some image receptor systems, and I think it's really important that we understand just the word phosphor. A phosphor is a material that can absorb energy, such as X-rays or laser light. It can then store that energy, and it can emit light when stimulated. What is a latent image? This is the invisible image created after exposure, but before processing occurs. We have two image receptor systems. You have computed radiography, CR. This uses cassettes and a cassette reader. We have to process these images manually. I take the X-ray, I grab my IR, my cassette, and I pop it into a cassette reader, and then it gives me a readout. Then we have digital radiography. This does not use cassettes or a cassette reader. I take the image is processed automatically. This is a faster process, and it produces higher quality images. The first one we're getting into here, this is computed radiography. The X-rays are hitting a photostimular phosphor. That photostimular phosphor, that PSP plate, it's going to capture the latent image. It's composed of extremely small particles which store and release the energy. The book, and this is one of the more common ones, it talks about this being made of barium fluorohalide crystals. So, in CR, the remnant X-rays interact with the electrons in the barium fluoride crystals of the imaging plate. This energy excites the electrons and allows them to leave the valence band. So X-rays come in, they hit some electrons that are in the valence band, and now that these electrons are having more energy, they're excited. They're able to actually break free of their valence band and move towards the conduction band. During this transition, many electrons become trapped in sites within the phosphor crystal known as F centers. So they're trapped in the crystals in these F centers. And that's where they're going to remain. That's where these electrons will remain, and they form the latent image until they're read by the reader. And this is an example of a multi-cassette reader. Then we have digital radiography. This is a cassetteless system. There's direct conversion, where the X-rays just go straight from X-rays to electronic signals. And then we have indirect conversion, where X-rays are first turned into visible light, and then that visible light is turned into an electronic signal. These systems use something called detector elements, DELs. And you can see that these detector elements, they're arranged in what's called a matrix, a series of columns and rows. Within these detector elements, you have your storage capacitor, your TFT, and you have right here, this is where the images are really taken, is in these pixel detectors. This is where they're received. So how it had the 80% by this fill factor, as your fill factor goes up, your contrast resolution is going to go up and your spatial resolution goes up. In this example, it's got a very small fill factor. So it has less contrast resolution and a lower spatial resolution. We're going to get into contrast resolution and spatial resolution a little further into this discussion. We're going to break down some direct conversion. This is a direct system with digital radiography. The X-rays hit a photoconductor made of amorphous selenium. That amorphous selenium emits an electrical charge. That charge is collected by the detector elements, and the thin film transistor, the TFT, is then able to release them to the analog to digital converter. So that analog charge is converted to an electrical signal, or a digital signal to be exact. Then we have the indirect conversion. There's two kinds of this: a charge coupled device, a CCD, as well as like the direct one, we have TFTs, we have thin film transistors. Notice both of these have a scintillation layer. So for the charge coupled device, the X-rays hit the scintillation layer, which the scintillation layer causes X-ray photons to be converted into light photons. And then these light photons, either by lenses or fiber optics for the charge coupled device, are sent to the CCD, and the light photons are converted into electrical signals. And that electrical signal is sent to the analog to digital converter. Once it's a digital signal, that is then sent to the computer and showed on our computer screen, or imaging display, if you will. Now we're going to talk about the thin film transistor. Same thing, it starts the same way. X-rays hit the scintillation layer. The photons are converted into light photons. These light photons go down to the photodiode. With indirect, this usually is made of amorphous silicone. Once that happens, it is converted into an electric signal. That electric signal is sent to the thin film transistor and the detector elements. The detector elements pick up the electric signal, and the TFT is able to send it to the analog to digital converter, which again sends it to our imaging display, which is for us typically a computer to monitor. A histogram, after this analog to digital conversion, it is able to go and be sort of processed, is able to be post-processed. So whatever anatomic body part we used is going to be what the reference histogram is going to be set up as. And all this digital data is going to form a histogram. It's really important that we choose the correct body part, because it's trying to do post-processing like processes based off of the histogram that's chosen. And if you were to scan an arm under what you're telling, if you select a chest and you scan an arm, it's going to be really confusing to the system whenever it receives this anatomic body part that it was not ready for. Automatic rescaling is a digital image processing function that adjusts the brightness and contrast of an image so that it appears consistent and uniform, even when the image receptor receives more or less exposure than ideal. The system analyzes the histogram and maps pixel values into an appropriate display range. Sometimes, even though the automatic rescaling, it does do a really good job, almost to a dangerous level, that underexposure and overexposure to an extent can sort of happen but still get a quality image. That's not an excuse to continue to underexpose or overexpose anybody. That's terrible practice. And sometimes there are artifacts that occur, one of these being quantum model. This is image noise that occurs when the image receptor does not receive enough X-ray exposure because too few photons reach the detector. The image appears what we call grainy, mottled, or rainy. This is most common in underexposed images in low dose techniques. So right here's an example of a bit of an extreme version of quantum model. It's just completely grainy. This is non-diagnostic, right? This is useless, borderline. And you can see, like, they show an example where a pathology was missed, and even then, it's just obliterated. Digital image display. Digital images are displayed on a monitor, and each image is made up of tiny picture elements called pixels. Every pixel carries a numerical value that corresponds to a specific shade of gray, ranging from pure white to total black. Shades of gray are going to be very important for us, and they're going to be with you for a long time while we are through this program. The number of possible gray shades a pixel can represent is determined by the image's grayscale bit depth. I'll give you the book definition of grayscale bit depth. It is the number of shades of gray that can be stored per detector element and displayed per pixel. It ranges from 8 bits to 32 bits. When we're talking about image quality factors, the acceptance characteristics of a diagnostic images kind of comes down to two main categories. There's the image signal factors. These determine the visibility of the image. And then there's image resolution factors. These affect things such as sharpness and the accuracy of the image. There's 4 primary image quality factors. So with image visibility factors, there's two of each of those categories we just mentioned. So image signal visibility factors, you have IR exposure, also known as signal value. Signal value is the proposed updated term, which kind of better reflects that digital images are created from electronic signals generated by ionizing radiation. And then with contrast, there's also a proposed new term, and that is signal differences. This is referring to how much the pixel values vary between tissues. When we're getting into the image resolution factors, you have spatial resolution, also called recorded detail or sharpness. All knowing these 3 terms go together is going to help you a lot in the coming year and a half, year and some change of this program. These describe how accurately the structural edges and lines of anatomy are represented. Then we have our contrast resolution. This is the ability to detect very subtle differences in signal values. This determines whether small differences between tissues can be distinguished from image noise. Image receptor exposure, the signal value, has a couple things that sort of make it up. This is mass, KVP, distance, which are the prime factors we talked about earlier. There's also patient factors, beam modifications, grids, and image receptors themselves. Patient factors, as subject density increase, the IR exposure is going to decrease. As something's bigger, if nothing else is changing, and the subject factor just increases, it's going to decrease your IR signal value. With beam modification, anything that changes the nature of the X-ray beam, other than the exposure factors already discussed, is going to be referred to as beam modification. There's 2 types. There's primary and scatter control. Primary modification, this is going to occur before the beam enters the patient. Examples of this are filtration and collimation. the amount of attenuating material required to reduce the intensity of the beam to half the original value is going to be referred to as the half value layer. The half value layer is expressed in millimeters of aluminum equivalency. Aluminum's the most common of the filtration that gets used, so that's why it kind of earned its spot here. And right here's the breakdown of how that looks. Scatter control. This occurs after the beam exits the patient. It involves methods to limit or remove scatter radiation before it reaches the image receptor. This can be used kind of accomplished with grids. I do want to talk about beam restriction and scatter. Beam restriction devices such as collimators not only improve patient protection, but they also do have a significant impact on image quality. When an X-ray photon travels through matter, there's a high probability that it's going to collide with an atom. This interaction can cause scatter, or it can cause it to lose energy. Scatter, and when I said scatter, I was referring to changing its direction. A photon that has been deflected or scattered off this way is known as scatter radiation. And why is scatter a problem? Aside from just that it could scatter off and hit you if you're too close, scatter photons do not carry useful information about the patient's anatomy. If scatter radiation reaches the image receptor, it's going to contribute to unwanted exposure, which we call fog. Fog reduces image contrast as well as overall image quality. And when we talked earlier about radiographic grids being a form of scatter control, this is a picture of sort of what a grid looks like. You can see it from the side view, and these dark lines right here, these are the lead strips. These are the vertical lead strips, and the space between them is the radiolucent material, such as aluminum or plastic. Radiographic grids use a plate of thin lead strips to prevent scatter from striking the image receptor. This improves image quality by increasing image contrast and also reducing the fog that the image receptor can receive. Absorbed and transmitted are fine for our image quality. Scatter radiation is going to reduce your image quality. Here, this is a grid in action. The X-ray photons traveling through the patient hits something, scatters off, then it hits this lead strip and it's absorbed. So that way it's not reaching the image receptor, which is down here. However, these spaces between the grid, between the lead strips of the grid, are radiolucent. So it's the X-ray photon is able to travel through the patient and make it through and hit the image receptor. These next couple of pictures are going to be give an example of how scatter can actually mess up our pictures and how it can fog it up. First one, this is great. You know, you can see the hand, you can see the spaces between the hand. Then what if we add a lot more flashlights? This could be an example of a scattered photon striking the image receptor. This didn't change at all. This part here did not change at all. All that happened is there's more just useless information coming in. And you went from being able to see spaces between the fingers, see outlines, to you just see a jumbled mess of a shadow. The grid ratio, this is the height of the lead strips to the distance between them. So here you have a 2 millimeter high lead strip and they're spaced apart by 1 millimeter. That's going to give you a 2-to-1 ratio, 2/1. Here you have a 2 millimeter high lead strip and they're spaced apart by 0.5 millimeter. 2/0.5, this is going to give you a 4-to-1 ratio. These are the most common ratios that we're going to be coming in contact with. You have a 5-to-1, a 6-to-1, an 8-to-1, 10-to-1, 12-to-1, and a 16-to-1. We're talking about grid frequency. This is another way that grids can sort of be labeled and categorized. This refers to the number of lead grid lines in a radiographic grid per inch or per centimeter. So most radiographic grids have frequencies ranging from 85 to 200 lines per inch, or LPI, or their equivalent in lines per centimeter. Image receptors themselves have characteristics that can influence IR exposure. Two important factors that with that are fill factor and image receptor sensitivity. These characteristics are inherent to the receptor design. They're already built in and cannot be adjusted by the technologist. The fill factor, this refers to the percentage of each detector element that is actually sensitive to the incoming x-rays. So earlier when we were talking about like the 80%, that is what this is talking about. A higher fill factor means a larger portion of the DEL collects signal, resulting in increased detector sensitivity and more efficient image capture. We like efficiency. Efficiency is basically always great. Receptor sensitivity. Sensitivity is determined by how much electrical charge the detector produces per incident X-ray photon before the collected signal is amplified. Higher sensitivity means more signal for the same exposure. When we're evaluating IR exposure or signal value with digital image receptors, the key factor used to evaluate proper IR exposure is going to be our exposure indicator. It's going to be the exposure indicator. The exposure indicator is a numeric value that represents the exposure the digital image receptor actually received during the exam. This is not a measure of patient dose. This is just the image exposure. When we're talking about exposure indicator values, the manufacturers that produce these digital radiography systems, they didn't all get together and decide to use the same indicator value, unfortunately. So there's currently no standardized method for calculation. You do have your exposure index, your EI number, and your EI number, it increases linearly and proportionally with exposure. Then you have your sensitivity number, your S number. This is going to decrease linearly and proportionally with exposure. We also have now a deviation index, the DI number. This is established by the AAPM, the American Association of Physicists in Medicine. This is crafted and is created to correct inconsistencies in exposure indicator values between these different manufacturers. This compares the actual exposure received by the digital detector to the target or the optimal exposure for that specific system and exam. This helps technologists evaluate whether an image is underexposed, properly exposed, or overexposed. Here's a chart. There's also some really good charts in your book, as well as tables that break down everything. Here you have the D numbers going from +3, which is it's excessively overexposed. And then you have it go down here to a -3, where it's excessively underexposed. We have our exposure latitude. This is the range of exposure levels that still produces an acceptable image. Digital receptors have a very wide latitude, meaning they can form a usable image from a broad range of exposure amounts. Again, this is something, while it's great, it's wonderful that these things, they can be so kind of user friendly. Still, we always want to be striving to achieve everything with the concept of LARA. We want to do it as low as reasonably achievable. There's the dynamic range, which is the range of exposure intensities that a digital receptor can detect, record, and process. This determines how much anatomical detail can be captured in both very light and very dark areas. There's data drop and detector saturation. Too much exposure can degrade image quality and lead to a condition known as data drop. Data drop occurs when digital detector elements, the DELs, become overwhelmed by excessive photon energy, causing a loss of signal during image reconstruction. If data drop affects a large portion of the detector, it results in detector saturation. Detector saturation is essentially regional or widespread data drop where entire areas of the image lose an anatomical detail because the detector can no longer accurately record the signal values. It's too high for it to record. Off the charts, if you will. There's windowing. This is occurring at the display monitor. Windowing is a digital image processing operation used to adjust brightness and contrast on the display monitor. You have your window level, your WL, window level. This is controlling image brightness. You're opening the window, you're letting the brightness in. Increasing your window level makes the image appear darker. Decreasing your window level is going to make it brighter. Then you have your window width. This controls image contrast, the range of grays seen on the monitor. A narrow window width increases contrast. It's more black and white. It's sort of like how the text here is completely black, and then it's just a white screen. That would be a narrow window width. And then you have a wide width. This is going to decrease the contrast. There's more shades of gray. They're less contrasting. It's not just white and black. There's, gray, light gray, slightly darker gray, slightly even more darker gray. It's a wider range. This is a bit of a breakdown of these concepts. The ideas of all this, it's going to be one of these that it follows us for a while. So let's kind of look into it now and hopefully start off on a good foot. You have narrow window width. You can see there's less shades of gray. It's white, couple grays, black. This is highly contrasting because there's such differences between the range in each one. It's also called short scale, short grayscale. Then we have wide window width. There's a wide variety. It's, gray, getting a little darker, 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 now black. This is low contrast. There's not as much differences between these shades of gray. Let's go down here. High contrast. There's few gray tones. It goes from minimum to maximum quickly. It goes white to black. It goes 0 to 100 real quick. This is also called short scale or narrow windowed width. Now we have low contrast, many gray tones. It goes from minimum to maximum slowly. This is like the car does not have a fast accelerator. It takes a while to get there. It's also called long scale because the scales are longer with low contrast. And there's wide window width. The image signal factor, contrast. Contrast refers to the difference between adjacent image receptor exposures recorded by the digital detector. These exposures range from highest to lowest and are best described using the term signal differences. So remember way back a little bit ago where all these other things we were talking about, the IR exposure or your signal value, now we've made it finally to the next one. This terminology more accurately reflects that digital images are composed of varying signal intensities rather than traditional film densities. Digital image contrast must be considered in terms of subject contrast, raw image contrast, and displayed image contrast. Displayed and raw image contrast. Subject contrast we're going to get into a lot on, so I want to go over these first. Displayed image contrast, the visible brightness differences between adjacent pixels on the monitor, determined by computer processing including lookup tables, automatic rescaling, and window width. This can be adjusted independently of the technical factors used during exposure. Then we have raw image contrast. This is the portion of subject contrast, which we're going to talk about in just a second, that is captured by the detector before any processing occurs. We have subject contrast. This is the range of differences in X-ray beam intensity after it passes through the patient. It is created by differential absorption between different tissues, bone or soft tissue. Bone's a lot more dense than soft tissue, so it's going to attenuate more than what the soft tissue is. It primarily depends on KVP as well as the amount and type of irradiated material. In our case, we're irradiating the patient. The patient is the irradiated material. There's other things that sort of play a role in subject contrast, such as contrast media, your mass, beam modification, image receptors and grids. All these have an impact. Low KVP, we have high contrast. It's going from the contrast is starkly different. It's going white, kind of gray, dark. Then you go to high KVP. High KVP is going to cause low contrast. These differences are not as much. It's going, gray, a little darker gray, a little darker gray. The amount and type of irradiated material. The amount of irradiated material is determined by both the thickness of the body part and the size of the X-ray field. When there are large differences between adjacent tissues, the differential attenuation is going to be greater, which results in higher subject contrast. Like looking at somebody's, like, the air in their lungs compared to their spine. That's a large difference. The type of irradiated material. This refers to the physical properties of the tissues being imaged specifically. The atomic number is going to help determine how strongly the tissue interacts and absorbs X-ray photons. And tissue density, which is the mass of tissue per unit volume, this is going to affect how many photons are attenuated. All right, we've made it to some image resolution factors. We're going to get into spatial resolution. Spatial resolution is the degree of sharpness with which structural images of an object are represented on an image. It is also described as sharpness of detail, definition, recorded detail. Again, these words, man, they're going to keep showing. This is affected by temporal resolution, beam geometry, and again, by image receptor characteristics. So let's break into temporal resolution a little bit and how it affects spatial resolution. Temporal resolution describes the relationship between the duration of signal acquisition, this is our exposure time, and the motion of the anatomy being imaged. The most common cause of a loss of sharpness is motion. Motion can be in a multitude of different ways. It can be voluntary, they're choosing to breathe, they're moving on their own, or it can be involuntary, such as the heartbeat or the peristalsis. Their intestines just doing normal intestine things. The best way to combat and kind of control involuntary motion is with short exposure times. The focal spot. Imagine shining a small flashlight on an object. Because the beam is narrow, it produces a sharp, well-defined shadow. Now compare that to shining a large floodlight on the same object at the same distance. The wider beam creates a blurrier, less defined shadow. This same principle applies to radiography, especially when we're talking about the focal spot. The focal spot is the area on the anode where the electrons collide. focal spot size, small versus large. A small focal spot produces sharper detail because the beam originates from a smaller source. Used when fine detail is important. When we're scanning a hand or we're scanning a finger, the small focal spot size is going to be the one we like. When we're talking about a large focal spot, this is going to produce less sharp detail, but it allows for a higher MA because it's larger. It can handle the heat. Remember, there's a lot of heat that's going to happen anytime an X-ray exposure happens. And this is going to be used for shorter exposure times, used for general radiography and larger body parts. The SID, we went a lot into some of the other stuff that the SID did earlier, but to build upon other things, you have the penumbra, the fuzzy edge of an object as imaged radiographically, also known as image unsharpness. The umbra, the true edge of an object as imaged radiographically. Less ID, so a lower SID, results in a more fuzzy image with a higher penumbra, and greater distance causes the penumbra to decrease, and then sharpness increases. The object to image receptor distance, this is your OID. When the object is moved closer to the image receptor, penumbra decreases and image sharpness increases. If you're noticing a trend here, when the penumbra is going down, your sharpness is going up. A smaller OID, a smaller object to image distance, results in better spatial resolution. We're going to get into distortion. Distortion is the misrepresentation of the true size or shape of an object on a radiographic image. Size distortion, the only form of size distortion that exists in radiography, is magnification. Magnification occurs when there's an increased distance between the object and image receptors. So you have a large OID, or it can also occur when you have an insufficient SID. Here, the one on the left, the source to image distance is causing the hand to look like this. The one on the right, the flashlight's moving in, the source is getting closer. Look at the hand. The hand's getting bigger. If SID decreases, magnification will increase. OID. Right here, this is our control. The hand's right here. The hand, it's moved closer. It's got bigger. The OID, the object to the image receptor, has increased. The hand's bigger. Right here, the hand's way now closer to the image receptor. The OID has decreased. The hand is smaller. We're going to talk about shape distortion. Shape distortion is determined by the alignment of the X-ray beam, anatomical part, and image receptor. This can sometimes be done purposely to demonstrate an area free of superimposition. Shape distortion includes things such as elongation and foreshortening. Influence factors are going to be central ray angulation, body part rotation, angulation, obliquity, or your IR alignment itself. This is kind of just a breakdown of those concepts in action. Here you see the IR is angled. We're having some elongation. The X-ray tube is angled. We're having some more elongation. And here the anatomy is angled, but these are not, and we're actually experiencing some foreshortening. The anatomy is appearing shorter there. We have some image receptor characteristics in regards to spatial resolution. The digital image receptors have characteristics inherent in their physical makeup that determines their spatial resolution limitations. Because these characteristics are inherent, the radiologic technologist, we are not able to alter them. They're in the image receptor itself. When we got some contrast resolution to talk about now. Contrast resolution is the ability to distinguish between subtle differences in image receptor exposures and differentiate them from noise in the image. It is affected by the image receptor contrast and subject contrast. Image receptor contrast. Image receptor contrast is the range of signal values acquired by the image receptor. It is controlled by the detective quantum efficiency, grayscale bit depth, and dynamic responses of the detector. Detective quantum efficiency is a measure of the sensitivity and accuracy of the image receptor, while grayscale bit depth is the maximum number of shades of gray each detector can handle. Dynamic response is the ability of a detector material to sense the incoming radiation. Alright, this took way more recordings and attempts than I thought it was going to. I certainly need to look into how to do recordings like this a little better, and to where if I don't catastrophically mess up or record 40 minutes of the thing without having my mic on, it doesn't just delete it all, because I don't know how to edit this stuff. Anyway, this is a lot of foreign concepts that are going to have to become unforeign to us. We need to learn them. I truly hope this helped. I hope y'all are studying hard. I hope you're, doing the best you can. I'm certainly rooting for you. This is not going to be the easiest test, but try your best. Learn as much as you can. If you do mess up, learn from what you messed up. Try not to mess up too much, though. Hey, what's this right here? Alright, that's it. Y'all have a good one.